Okay. So today is gonna be like a much more calm meeting. Um, and the idea with what we're gonna do today is just so okay, we talked about like what a manifold is. We talked about like vector bundles on manifolds. We saw how to define a manifold using cocycles. But all of this is not useful if we don't have any examples of what a manifold is, right? Like we know the definition and that's wonderful, but like at the end of the day, we want to do physics, right? So we want to know if manifolds are actually even the right choice of object to work with. And so the 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 very important question is like, what are things that are manifolds? Like, what are examples of things that are manifolds? Um, and that's the thing we're going to talk about today. So we're going to talk about mainly we're going to talk about examples of manifolds. Um, but before we start talking about examples, I do want to get a couple theorems out of the way because they're important um, in the sense that they allow us to define manifolds without having to use charts. Okay. So if you remember from earlier, the way we defined a manifold is you take some topological space, that's Hausdorff second countable, um, and then you take a collection of charts on this um, manifold, and then you have some like compatibility condition on the intersections that like the change of coordinates have to be smooth. Um, and sometimes that's a perfectly reasonable way to define a manifold. As we saw when we defined fiber bundles, it was more natural to, start with some base manifold, define some cocycles on it, use that to then define charts on a new manifold that we're constructing, and then get charts out of that. But other times that's not the best way to go about it. And a nicer way would be the way we did it in like multivariable calculus, where it's like I have some function, and then I look at, the regular values, and then I look at level sets of this function. And then level sets of this function turned out to be manifolds, right? So that already gives us a huge range of hypersurfaces, um, like hypersurfaces in Rn. But we want to, generalize this a little bit. So just to do this, um, we're gonna define some things that um, are already generalizations of things people have seen in multivariable calculus. But I guess you've never actually called it that. So here's the setting. So let f from n to n. So m and n are smooth manifolds as always. Um, be smooth. Okay. Um, then f is called an immersion um, if for all points in the manifold, the differential uh, is injective. Uh, let me is injective. Okay, so yeah, basic definition, if the differential at each point, so you can think of the differential in multiple ways. You can think of it as maps between tangent spaces. You can think of it as a matrix in like the matrix of partials in a coordinate system, however you want to think about it. And then if that corresponding map is injective, then the for every point, then the function is called an immersion. Okay. Um, F is called F is called a submersion if for all points the differential um, is surjective. Okay. Is surjective. Okay. I mean, again, standard definition. F is called a local diffeomorphism if for all points this the differential is bijective. Okay. So the local diffeomorphism, it's called a local diffeomorphism because you can use like inverse function theorem to get a to get the fact that the map will be locally invertible. So in some sense, you're mapping some small enough neighborhood of your point diffeomorphically to a neighborhood of the image. And so these two things are now diffeomorphic. Okay. So in other words, a map is a local diffeomorphism if it is both an immersion and a submersion. Okay. One thing to note is that local diffeomorphisms may not be diffeomorphisms. Okay. You can have non bijective local diffeomorphisms. Um, yeah, that's just one thing to keep in mind. Um, Immersions and submersions may not be injective or surjective necessarily. Um, so yeah, I mean it's the same thing, right? Just because the derivative is injective doesn't mean that the original function is also injective. Um, so so there's that. Okay, so with this out of the way, um, let let Q be a point in the image. Okay. Uh, and the image is a subset of the codomain. Um, then Q is a regular value if for all points P in the preimage of Q, um, dfp from the tangent space into the tangent space is surjective. Okay. So essentially, if you restrict the function f um, to the level set of Q, then the map is a submersion. Okay. So then Q is called a regular value. Otherwise, it's called a critical value. Okay. Okay. So with this out of the way, let's now define one more thing. So um, let S be a subset of M. Um, then S is called a k-dimensional submanifold of M if for all points P on S there is a chart U phi a chart um, such that for all Q in U, do I need that? No, that's just such that phi of U intersect S is equal to phi of U intersect R K. Okay. So the idea is that it's a submanifold if at each point I can find a chart um, so that the last n minus k entries are zero. Okay. So in other words, it's sort of a generalization of the idea that Rk sits inside Rn, like naturally. Um, One thing you can check now as an exercise, it's not a very hard exercise. You can check that submanifolds are manifolds in their own right. Okay. Um, and what this means is that you have to find charts for S, okay, um, that are k-dimensional. Um, and yeah, you can check that you can check that it's not very hard to prove. Are there any questions so far? Okay. Um, Now we can use the implicit function theorem. Implicit function theorem to show that if Q is a regular value for F, then the preimage of Q is a submanifold of dimension dim m minus dim. Okay, so this follows relatively quickly from the implicit function theorem. Okay. Okay, so with all of these preliminary definitions and theorems out of the way, the main one being this one, um, of this is called the regular level set theorem. So the above is called regular level set theorem. Okay, so we're gonna now use the regular level set theorem um, to define most of the manifolds that we're gonna see. Okay, so let's start easy, So now let's go into examples. Okay, so the first one, I mean, trivially, Rn. Okay, everyone's favorite Rn is a manifold. Along with Rn, any real or complex finite dimensional vector space can be made into a manifold. Um, and the idea is really simple. All you do is you take a linear isomorphism between your vector space and either Cn or Rn. You take um, you take the you basically force it to be smooth. And forcing it to be smooth will, make you um, will give you some structure, like topological structure on it, which you can then um, use to get charts. Okay, so that one's a very simple example, right? Like that's not too hard to see. Now let's go into something more spicy. So GLNR. Okay. Actually, before we go into GLNR, um, so I'll go in a slightly different order than what I have in the meeting notes or whatever, because I for some reason I overlooked this example like way early. So let's look at let's look at let f of x sorry, let f go from Rn plus 1 into Rn, into R, given by f of x equal the norm of x squared. Okay. So this function is smooth almost everywhere, right? This function isn't smooth at 0 because it like comes into a cusp. Um, but we don't care about that, right? So let's just pretend like that point doesn't exist. Now let's look at let Sn, whatever Sn is, be the preimage of the point 1. Okay. So in other words, Sn is the set of all x in Rn plus 1 so that the norm of x squared is 1. In other words, this is the unit sphere. Yeah. Um, and if you remember when I defined what a manifold was, I said the sphere is a manifold. And I also said that you can define charts on it to show that it's a manifold. But this is another way you could do it. Now we have to show that for every point in, for every point um, in the level set, df p from tp rn plus 1 into t at 1 of r is surjective, right? We have to show this. But what is the differential at this point? Um, you can convince yourself that df at p, right, evaluated at a point v. So one thing to note is that the tangent space of like Rn is just Rn, right? So you can just now think of the differential as taking in vectors from Rn and giving you a number. Um, and you can now just think of this in your like um, regular way of taking derivatives. Um, and we see that the differential at the point P of f is the linear functional 2p1, you know, 2pn plus 1. Okay. Um, you, it's not hard to see why, right? Like this step is fine. Because I mean, this is just partial f partial x1, right? So if you write out f of x, um, if you write out f of x, so f of x is equal to the sum as I goes from 1 to n plus 1 um, of xi squared. Now if I take xi squared, now if I take the partial of f with respect to xj, what I get is this is the sum as I goes from 1 to n plus 1. And then I have to take the derivative of this thing. But if xi and xj are not the same, I get 0. So I have a delta ij times 2 um, xi, right? This is just a chain rule, uh, product rule, um, which just gets me 2xj, sorry. But now I'm evaluating this at the point P. So this just becomes so partial f partial xj at the point P is just 2pj. Okay. So however you want to write it. And let's put it up because I've been putting it up. Okay. But this map is clearly surjective, right? This map is clearly subjective because this vector is not zero. Okay. The reason this vector is not zero is you have to remember the norm of p squared is 1. Right? So since norm of p squared is 1, this implies that pi equal not equal 0 for some I. Um, for some I. Because if it was 0 for all i's, then this thing would just be, this norm would be 0. So what this tells me now is that, okay, we have that the map is surjective for every point in the level set. That means that 1 is a regular value, and hence the sphere is a manifold. Okay. Another thing is the dimension is very easy to compute because you take the dimension of this thing and you take the dimension of this thing and then you subtract, right? Of dimension 2n plus, sorry, n plus 1 minus 1. So it's just dimension n. Okay. Are there any questions like regarding this? Okay. because this is a very, very important example, and it'll this serves as like the stepping stone into like how you use the regular level set theorem to generate a bunch of manifolds. Okay, so let's move on. Let's look at GL and R, right? This is, if you remember, this is the space of all matrices from Rn into Rn, such that A is invertible. Um, and now you can check that this is open. This is open. Okay. And the way you can check this is that this is the preimage. Uh, this is the preimage of the determinant function on this open set. Okay. So since this thing is open and you know that the determinant function is smooth, the reason you know it's smooth is because it's a polynomial, right? The determinant is a polynomial, so it's smooth. And this is open. That means GL and R must be open. Because remember, the topological definition of continuity says that function is continuous if and only if the preimages of open sets are open. And since you know beforehand that the determinant is smooth, you know this must be the case. Um, and now, since this is open, um, it is a submanifold, okay, of dimension. So it is a submanifold. So GLNR is a submanifold. Um, is a submanifold of Rn squared and has dimension n squared. Okay, very simple. Okay, are there any questions regarding this? Nope. Okay. Now let's move on to the next example, and that is SLNR. So SLNR. If you remember, this was the subgroup of GLNR, such that A is an SLNR if and only if if and only if the determinant of A is 1. Okay. So I think this equation alone already should tell you how we're going to show that this is a submanifold. Right? We're going to look at the determinant function. We've already convinced ourselves that it's smooth. Okay. So all we have to do now is we have to show that the preimage. So now we need to show that um, for all A in determinant inverse of 1, which is equal to SLNR, D of the determinant at A from the tangent space of GL and R into the tangent space of 1 and R. Remember, the tangent space of GL and R is just going to be Rn squared, and the tangent space of R is just going to be R. So you're looking at the determinant, um, the derivative of the determinant at some point in SL and R, um, as a map from Rn squared into Rn. Sorry, into R. Um, if you if you've seen the problem, like the problem sheets, I ask you to find the derivative of the determinant at the identity. And if you've done that problem, you should know that the derivative of the determinant at identity is just the trace. So that's really cool. We'll also see near the end of today's meeting how we can take the tangent space of at the identity of a subgroup or a Lie subgroup of GLNR and transport that into like the tangent space of something else. Okay, but for now, let's try to show that this is injective. Um, and the way we have to do that is we just have to show that um, this map is not, sorry, this map is surjective. Um, And the way we have, since this is a map into a one-dimensional vector space, all we need to do is show that this map is not zero. Okay? Do we get why that's the case? Okay. So the way we're going to do this is we have to plug in a tangent vector into this, right? And get a number. So since the tangent space is Rn squared, we're going to look at the line that, like the straight line that goes through the point A with speed A. Okay. Sorry, with velocity A. So consider gamma of t equals A plus TA. So in other words, you can think of this as the directional derivative of the determinant at the point A in the direction A. Okay. Um, so this um, this means that if you take the derivative at the origin, sorry, not at the origin, derivative at zero, um, you just get A. Okay, so the tangent vector this corresponds to is A. So we're at the point A, we're moving in the direction A, and now we're going to compute the derivative. So we have the derivative of the determinant at A evaluated at A. This is just, if you remember the like definition of um, the derivative functional. Okay. Um, and then from here, it's very simple to compute because this is the determinant of, so if I factor out an A, I get a 1 plus t times A over here. And then I factor out the 1 plus t, so I get a 1 plus t, 1 plus t to the n times the determinant of A. And then now evaluating this derivative is not hard at all. This is just n. Because remember, the determinant of A is 1. But n is not equal to 0. And since it's not equal to 0, um, this differential must be surjective. Okay, so hence 1 is a regular value for determinant, which tells me that SLNR is a submanifold of dimension n squared minus 1. Okay. Are there any questions regarding this?
No.
Okay. Okay, so we've looked at SLNR, we've looked at GLNR, these are groups that come up frequently, often in everything from like math to physics. Um, so it's good to know that, okay, at least these things that were examples of like Lie groups are at least manifolds, or at least we've proven that they're manifolds. Because before we were just taking the fact that they're like subsets of Rn, and they're nice enough subsets of Rn, so um, they must be manifolds. But now we've actually shown that they are. Um, let's now shift our focus to a group that isn't too talked about in physics at U of T for some reason. Um, but it is nonetheless very important to the study of physics. And those are the orthogonal groups. Okay. And if you remember examples of orthogonal groups, I mean, the examples of things in the orthogonal groups would be a rotation, right? They preserve inner products. Um, and rotations are one of the most important things that, we study as physicists. Um, because they're one of the easiest um, transformations you could apply to a system, right? Just rotate all your apparatus. Um, okay, so Let's just define a couple things. Okay, so remember, keeping special relativity in mind, um, when we look at orthogonal groups, it would be a bit counterproductive to just think of, the usual orthogonal group, which preserves the inner product, or the usual inner product. Um, or in other words, you have A transpose equals A. Sorry, A transpose equals A inverse, right? Um, so keeping special relativity in mind, we actually look at more general bilinear forms. So let G, you know, let's call it G, be a non-degenerate, non-degenerate bilinear, symmetric bilinear form. Bilinear form. Okay. And the way we're going to define this is going to be like, okay, so it's G of xy equals, um, let me actually call this map, I'll call G. Um, and then you'll see Y. So, okay, we have this, and it's going to be X transpose G Y. Okay. So G is, sorry, this should be G, this is Y. So G is some uh, symmetric matrix, uh, okay, symmetric matrix. Um, so now, G has signature PQ. And if you remember what that is that um, a non-degenerate bilinear form has signature PQ if you can find a basis in which the norm of P vectors is 1 and the norm of Q vectors is -1. I think the existence of such a basis is called Sylvester's law of inertia. So you can look that up if you need a proof of why this is a well-defined thing. So I'll just put that here. Look at Sylvester's uh, law of inertia. Okay. And now, so what is the corresponding orthogonal group, right? Because we wanted to talk about the orthogonal group. So the orthogonal group OPQ is going to be the set of matrices in GLNR um, that preserve inner products. So such that G of xy is equal to G of ax ay. Okay. And you can see from this definition alone that the condition that A, B, and GLNR is not needed. And the reason for that is if A was non-invertible, you would have something that gets mapped to 0. And then you can take that and then take its norm and you just get 0, which would then imply by non-degeneracy that the vector itself was 0. So you can prove that A is invertible if it preserves inner products, it has to be invertible. Okay. So looking at this another way, you have A is in OPQ if and only if A transpose GA equals G. Okay. And this is very simple to prove because this is equivalent to X transpose A transpose G A Y equals X transpose G Y, which is equal to G of XY, and this is equal to G of AX AY. Okay. So you can see it's very easy to prove why this is the case. Okay. Okay. So with this, now let's consider. So consider the map F from Rn squared into the space of symmetric n by n matrices um, by F of x equals um, x transpose. Okay, just to keep in mind with my notes, it's A transpose G8. Okay. Now you can actually show that the space of symmetric n by n matrices is a vector space. Okay, so I'll leave that as an exercise. Show this is a vector space of dimension n times n plus 1 divided. It's not too hard to show this. Um, but yeah. Um, I might actually put this on a problem sheet. I'll put it on a problem sheet. And maybe I'll give a hint or two if needed. Um, okay. So now, okay, since this thing is a vector space, and our first example of manifolds were vector spaces, um, it makes sense to talk about the map being smooth, this map F being smooth. So let's talk about why this map should be smooth. Um, So if you look at the components of F, right, they're just polynomials in A, right? So by matrix multiplication, everything is just a product and sum of the components of A and G. But G is constant, so let's forget G. A is the thing that changes. So um, it's a polynomial in the entries of A. And since it's a polynomial, it's smooth because we know polynomials are smooth. Right? Okay. Are there any questions on why F is smooth? If you've seen a lot of these things just boil down to the fact that like, okay, we already know that this function is smooth because it's a polynomial. Um, so that's cool. Okay, so now what we need to note is that OPQ is just the preimage of G, right? Because if you remember, G is a symmetric n by n matrix, which means that it lives in this space of symmetric n by n matrices, right? Um, and hence the orthogonal group that corresponds to G is the pre-image of G. Okay, so what we have to do now is we have to show, so excuse me, we need to show that for all A in OPQ, um, df at A from Rn squared into the symmetric n by n matrices is surjective. Okay, so let's do this. So to do this, we first need to compute the derivative. So, so let's compute the derivative. So df of A at some vector x is d by dt um, of f of A plus tx, because this is a curve that goes through A, has derivative x, lives in your space, blah, blah, blah. And then, just computing this out, we get the following. Um, I'll skip a few steps because they're not particularly enlightening, to be honest. Um, so you get A transpose G A plus T times A transpose GX plus TX transpose GA plus T squared X transpose GX. Okay. And now taking the derivative, this term goes to zero because it's constant. This term goes to zero because it has a t squared, and when you evaluate it at zero, it kills it. This t vanishes, and what you're left with is A transpose GX plus X transpose GA. So you're left with A transpose GX plus X transpose G. Okay. Now let Y be a symmetric n by n matrix. And now our goal is to find a vector X or a matrix X such that when I put it into this, I get Y. Right? Um, and the obvious choice, not obvious. I mean, it's obvious once you see it, in my opinion. The obvious choice for Y is for X is the following. Then let X equal 1/2 A G inverse Y. Okay. We'll see why this is correct, the right choice. Then note this. This implies that the differential of x, sorry, of f at a evaluated at x is just a transpose g times 1/2 a g inverse y plus 1/2 y transpose g inverse transpose a transpose um, g a. Okay. But now remember, G is a symmetric matrix. Its inverse is also a symmetric matrix. Hence, G inverse transpose is just G inverse. Okay. So if you're not convinced with that, let's it's easy to prove. So we know that G inverse is equal to the identity. If I take the transpose of both sides, I get G inverse transpose G transpose equals the identity. Right? Because the transpose of the identity is just the identity, which then tells you that G inverse transpose is the same thing as G transpose inverse, but G transpose is just G, so it's G inverse. Okay. Um, so what this tells me is that this is A transpose G, so it's sorry, it's I'll factor out the 1/2, so it's 1/2 times A transpose GA times G inverse Y plus Y transpose G inverse A transpose GA. Okay, but what was the defining characteristic of A? It's that A transpose GA is just G, right? So what we're left with is this thing becomes G. Um, this thing becomes G. So you're left with G inverse Y plus Y transpose. Um, oh yeah, also Y transpose is just Y, because Y is symmetric, remember? So you're left, so that you get rid of that. That becomes Y. This becomes G inverse G. But G inverse G is just the identity, so you're left with Y. Okay. So what we've now done is shown that for any symmetric n by n matrix, there is a corresponding n by n matrix, so that when we put it into the derivative, right, you get that symmetric matrix. In other words, we've shown that um, df at A is injective. Sorry, surjective. Okay. We've shown that it's surjective. What this means is that hence, right? So we've shown that it's a regular value. In other words, we've shown that it's a regular value, which then means that the orthogonal groups, all the orthogonal groups that we can have, okay, are manifolds. Manifold of dimension n squared minus n times n plus 1 divided by 2. And then you can compute that out and convince yourself that it's n times n over, say, n times n minus 1 over 2. Okay. Are there any questions? Okay. So let's ponder this for a second, okay? Because this is something that's very important to understand. So we 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 started with the definition of manifolds, and I told you that at least for classical mechanics, manifolds um, are the most optimal place to do physics, right? At least in the classical sense. Um, and then I went off and we talked about like group actions. Um, we talked about Lie groups. We computed some Lie algebras. Um, and now one might think that everything we've done is pretty pointless because we haven't actually shown that Lie groups exist or any object that we're familiar with are Lie groups, right? So what exactly was a Lie group trying to do? Um, and I think the last couple of examples really show you why Lie groups are in fact something that we should study because even in terms of physics, we care about the orthogonal group. We care about the fact that um, physics is like invariant under the action of certain orthogonal groups or certain subgroups of the orthogonal groups. Um, so it would be very good to be able to do calculus with them, right? Because we want to change. There might be situations where we change how um, the action is applied. We change our apparatus over time. There's so many things that we can do. So it would be wonderful to do calculus on these groups, right? Um, and just with that, we've shown like a bunch of the orthogonal groups that we cared about before um, are now Lie groups. You can convince yourself that these are Lie groups because matrix multiplication descends into, a smooth function on these manifolds. Yep. Okay. Um, so now moving on to six. This is actually more like 5B. So I'll call it that. And I'll call it six. SOPQ, which is a subgroup of OPQ given by um, A in SOPQ if and only if the determinant of A is 1. Um, and A is in OPQ. What this tells us immediately, hence, firstly, this tells us that this is a manifold. This already tells us that this is a manifold. And the way you can prove this is you can look at f of A given by A transpose GA and the determinant. And we showed that each of these are submersions. And since each of these are submersions on the corresponding spaces, this whole map is a submersion. Okay. Um, is a submersion on SOPQ. What this implies is that SOPQ is a manifold of dimension um, n times n minus 1 divided by 2 minus 1. Oh, very simple. Um, yeah, we just directly showed that this thing was um, a submersion. Yeah, okay. So yeah, the idea is the same that f comes from Rn squared and goes into symmetric n by n matrices times the real numbers. Um, this is a manifold. You can convince yourself that this is a manifold because again, it's a vector space, so it must be a manifold. Um, and yeah, okay. So, are there any questions for why the special orthogonal groups are Lie groups? Like, does it at least make sense?
Yeah, it does, I think.
Okay, you sound a little unsure. So let's take a step back and let's try to, go through like why. Um,
Mhm.
like, is there
Um,
anything specific you think that's?
let me see. I think I just have to stare at it for longer. It's okay.
Yeah, I think I think like if this because the first time I saw it also it was not the easiest thing to wrap my head around for
Mm,
sure. Um, and that's mainly because we're somehow concluding that this like smooth information, right? Like this information about the derivative is giving
yeah.
me topological information, right? Because being a smooth manifold has nothing to do with smooth functions necessarily. It's all about the topology of your space, right? The topology in itself gives you smooth structures rather than smooth structures dictating topology, right? You can't have one without the other, kind of.
Yeah.
So I think one thing that you could do to like help yourself understand this is understand the regular level set theorem.
Mhm.
Okay. Because I think that's where most of the magic is actually happening. So understand the implicit function theorem, understand the regular level set theorem. Um, Eckhart's book again is very good for all of this. Um, at least that's where I learned it for the first time, and I thought it was pretty good. Um,
Mhm.
so Eckhart's book is a wonderful place to start. Um, but I think you do a variation of this in 237 as well.
Yes, we did. We
Okay.
did implicit function theorem, but it's in terms of the Jacobian and stuff. So,
Yeah, so if you remember the implicit function theorem, you have like the Jacobian matrix, and then one part of it is like non-singular,
yup.
right? And then you can write these variables in terms of these variables,
Yes.
right? That's the idea of implicit function theorem.
Yup.
And what I'm saying now is that, like, okay, with that in mind, and the fact that, okay, like submanifolds are submanifolds, um, this thing on its own, I think, if you stare at it long enough, should tell you that, okay, if I have a submanifold and I take, like, if I think of it as a map, right, I have that some parts are non-zero and the
Mhm.
others are zero. So using some implicit function magic, I can write the things that are zero in terms of the things that are non-zero, right? Um, and that's actually exactly what goes into proving the regular level set theorem. Rather than proving it for, general manifolds, what you realize is that this is a local statement completely, right? So all you care about is like, at each point, can I find a chart? Right? And finding a chart is just equivalent to solving systems of equations, which implicit function theorem allows you to do. So that's why I'm
Okay.
saying, like, I think the best thing you could do is you could go like open up Eckhart's book, um, and I don't know if like Lee's smooth manifolds book. I don't remember if he does it. He probably proves a regular level set theorem, but I haven't seen the proof,
Mhm.
how he does it in that book. So, but Lee is, I mean, like a gold standard for introductory differential geometry. So, that's something to check out as well. So, so yeah, and then once you have that in mind, like understand how I'm taking these derivatives, why I'm choosing the things that I'm choosing, because I think this choice is also important. How I've taken, like, why did I choose this curve and not some other curve? Does it matter that I chose this curve and not some other curve? And the answer is no, it doesn't actually matter, stuff like that. Okay. But yeah, okay. So we've shown that like some of the most important groups and sets that we've worked with are in fact manifolds. Um, but okay, I'm saying this is useful in physics, but I haven't really talked about why. So let's talk about that, right? So, excuse me. Hold on one second. Okay. So in special relativity, so in special relativity, um, we have the metric, or we have the inner product. Um, Physicists usually call this eta. VW. Oh my God. VW, and it's given by V0 W0 mine how do I want to do this? Okay, let's do it like this. Right? Like this is from special relativity, we know that this is true. Another way to write this is how I did when I was proving that these things are manifolds, and it's by looking at the matrix version of this. So it's negative one, one, and one's everywhere, right? So so we can see this. So if we want Lorentz invariant physics, we want to study um, the Lorentz transformations, right? Like we want to study Lorentz transformations. Um, and if you recall, Lorentz transformations were given by the general Poincare group, right? But let's not worry about the Poincare group. So let's look at a smaller subgroup, and that's the Lorentz group. And it's just the like all the Lorentz transformations that we can do that don't involve boosts. Or do they involve boosts? Sorry, that don't involve translations. Okay. So the Lorentz groups, so the Lorentz group um, is the group SO plus um, 1, 3. Okay. Well, I guess SO plus 3, 1. It doesn't actually matter. SO plus 1, 3 and SO plus 3, 1 are the same. Um, but okay, what is this group, right? So we haven't talked about this group specifically, but we've talked about SO13, SO31, whatever you want to call it. Um, so not the following, right? So um, if you look at O31, right? If we look at O31, these are just all transformations that preserve um, the Lorentz group. Sorry, not the Lorentz group, the inner product. But we care about a smaller subset of this, right? Because, for example, we don't want reflections in time, right? Like we want time orientation to be kept the same, right? So that's what this plus is over here. It's the orthochronous uh, um, subgroup of the orthogonal group. We also want things to preserve orientations in space, right? Like we don't want to reflect along an axis or something like weird thing like that, right? So that's also encoded in this plus. And then finally, we care mainly about determinant one. Things similar to like why when you're looking at rotations, like scaling and then rotating is basically the same thing as like rotating, right? So it's good enough to look at the special orthogonal group, but also the ones that preserve time orientation and space orientation. So that's what this thing is. Okay. Oh, oops. Um, okay. With that out of the way now, we can talk about the dimension of this object. Um, so so note that 031 has dimension um 4 times 3 divided by 2 or 6. Okay. So this is I'm very sloppy right now. So this is the dimension of this is 4 times 3 divided by 2, which is 6, which then means that the Lorentz group has dimension 5. But actually that sounds wrong. Hold on, let me just check. Hmm. Okay, I misspoke a little bit. So the Lorentz group is 031, um, and the restricted Lorentz group, is the one we talked about, SO plus 31. Right? This is the one, this is, you can think of this as the identity component of this. And what identity component means is that you look at the maximal connected set, connected open set that contains the identity. Okay. So, um, like this group looks something like that. Identity is in one of them. So you just look at this one. So okay, there's actually two exercises here. So exercise one, show that this group has four connected components. Um, this isn't, I don't know. I haven't actually proven this, so I don't know if it's hard or not. It might be, it might not be. I don't know. But I do know for a fact that it has four connected components. Um, not only is it not only that, you also should show that um, the so let G be a Lie group and N be the connected component of E, then N is normal in G, and N is a submanifold. The submanifold part is easy because it's open. So by definition, it's going to be a submanifold. Um, Showing that it's normal is a little harder. Um, but it's not. Yeah, just let me know if you need a hint for this one at least. I've done this problem, so I know if it's hard or not. Um, it's not hard if you remember the definition of normal. So I recommend you um recall the definition of normal. Okay. Um, so yeah, okay. So the main physical the main group we care about in physics is the restricted Lorentz group because again it preserves time orientation and stuff like that. Um, if you remember one of our like first meetings, we talked about how the fundamental group of the special orthogonal group in 3 dimensions gives rise to a double cover called the spin groups, right? Um, so sorry, let me say that again. So the fundamental group of the special orthogonal groups in Rn um, give rise to spin groups, right? Similarly, the fundamental group of this thing also gives rise to spin groups of signature 3, 1. Okay. So, well, actually, signature 1 or n minus 1, I guess it would be. So the idea again is like we can think of spinners not only in like um, the Galilean sense, where like, we rotate twice to get back to where we were. Um, I don't have a similar like pictorial analogy for what um, the spin groups, like the Lorentz spin groups are. Um, so so yeah, I'm not exactly sure like how to really say much about this, but we have the spin groups spin 1, 3, um, and turns out that which is the double cover of SO 3, 1. We won't talk about this one so much just yet. So if we want to go into like the spinner part of the reading group, we might go into it like later on. But for now, this is again just something to keep in mind, similar with the spinners and n dimensions. It's just something you should keep in mind. Um, right, and then this turns out that this is isomorphic um, to the space SL2C. Okay, so this is the special linear group over the complex numbers. Um, and it is also isomorphic to the symplectic group that we have not talked about. We will talk about this when we talk about symplectic geometry. Um, okay. Are there any questions? Okay. Um, so I was planning on computing some tangent spaces. Um, do you want like I do you want to see them or should I wait for next time? Well, how are we feeling?
Okay, just do one example.
Okay, okay. So let's do the example of a sphere for now so that then we can like um and we'll continue next time. So
Okay.
so we've proven that the sphere which sits inside Rn plus 1 is a manifold, right? Um Moreover, so if we look at the function I, right? Um which is the inclusion function, so Sn into Rn plus 1 mapping x to x is smooth, right? Well, it's clearly smooth because it's a restriction of identity, right? So it has to be smooth. Um, so what that means is we can look at the tangent space of this, right? And we can look at the image um, of the tangent space. So we can look at the image. Um, yeah, we can look at the image of the tangent space sitting inside of the tangent space of Rn plus 1. So what this means is we can look at the tangent space of Sn to just be a subset of Rn plus 1. Okay. That's the main idea that I'm going for. And now it's an exercise. Exercise. If um, a manifold, um, okay, if F Mn is smooth and F inverse, which so we have a regular level set, is a regular level set. Then the tangent space, so TP F inverse. Let me call this thing S. So the tangent space at a point P of S is just equal to under the identification, by the way, like equal to the kernel of the differential. No, that's not true. Is the kernel? Wait, I think I have a typo here.
Okay.
This should be kernel of the differential map at the point P. I will fix that in my notes. Okay, so yeah, let's try to reason our way through this. Um, if you have a level set, right, and you move in any direction that goes outside of the level set, right, then the function changes because it's not constant. You're not on the level set anymore. It changes. So that means the derivative can't be zero. But if you're on the level set, the function is constant. So when you take the derivative, it's zero, right? So so taking derivatives in the direction of the manifold, of the submanifold, should give you zero, right? Of the function, because does that make sense? Right? So I mean, like, think about it. You have a function that it breaks up the domain into a bunch of level sets. If I move from one level set to another level set, I've changed the value of my function. And since I've changed the value of my function, any derivative along that direction has to be non-zero of this function, right? But now if I'm along the level set, the function doesn't change value, so its derivative is zero. So things tangent to my manifold have to give me zero derivative for this function. Yeah. Okay, so with this, let's now look at so again, if you remember this is, I think, exercise 2 in the second problem sheet. I asked you to show that um, the velocity of a curve on the sphere is perpendicular to the curve itself, right? And that's reflected in this because okay, so this tells us that TPSN is equal to the kernel of DFP, where DFP is equal to 2 times P1 Pn plus 1. But if we write this out, DFP of V, where V is in Rn plus 1, right? This is nothing but 2 times the dot product of P and V, right? Because I get P1 times V1, Pn plus 1 plus Pn plus 1, and so on. Um, but this equals 0. What that tells you is that V is in the tangent space of Sn if and only if. So, so hence V is in TPSN if and only if um, P dot V is equal to 0. Okay. Um, so yeah, this was an example of a computation. Um, the next meeting, which is on um, Saturday, um, we will compute. So next time we compute, we'll compute the tangent space of the orthogonal group. Um, we'll also compute the tangent space at identity of the special linear group, um, which will then lead us to the tangent space of the special linear group at any other point. Um, and yeah, that's it. We'll do those examples mainly. Um, I might look into the tangent space. Oh, never mind. Okay, okay. I was gonna say I might look into the tangent space of the Lorentz groups, but we're already doing that here. Um, so yeah. Are there any questions?
Nope.
Okay. Um, so yeah, by Saturday, let me know which one you're feeling more, like which direction you're feeling a little more. Um,
Okay.
if you're feeling like, you know, GR, or if you're feeling like spinners. I'm mostly leaning towards spinners for now.
Mm.
Um, but that might change if you guys want, like if you guys want it to change, then that might change.
And
Uh,
why do you prefer spinners over general relativity?
I mean, it's just like the part of math I'm more interested in. Um,
Mhm.
like, it's more, I want to choose my words carefully here because
Okay. I mean, it's just two of us, so just you can just say whatever.
I don't want to like give a misleading picture. Like I don't want to say like I don't know. I was gonna say something like it's more geometric, but that's not necessary. That's not true. Like in the slightest.
Oh, yeah, I thought general relativity is mostly differential geometry, right?
Yeah, yeah. General relativity is mostly GR. It's actually it's actually mostly Lorentzian geometry,
Mm.
which, funnily enough, where we won't even get to. Um, Yeah. Well, we'll talk about its cousin, like Riemannian geometry.
Oh yeah,
But we
that's
won't. So if we do GR, we'll talk about Lorentzian geometry.
mhm.
Spinor geometry is also something that I know more of than like I don't know that much Lorentzian geometry, so that's another thing.
Mhm.
Like I'm because even in my like GR, if you take 484, um at least the way we did it is that we had like a final project at the end. Um, and I just so happened to choose spinners.
Oh, okay.
So so I just know more of spinners, like I know more about spinners. Um,
Yeah, yeah.
um, and some of the math used to like deal with spinners is also like pretty cool in my opinion. Um, if you know who like Sir Michael Atiyah is, um, so he's a mathematician who revolutionized basically revolutionized spinor geometry. Um, and he has like a very famous, very important theorem called the Atiyah-Singer index theorem. Um, that is like one of the most important results, yeah, that's come out of geometry, or like the intersection of geometry with other stuff. Um, and yeah, even and there's a talk where he like talks about like um spinners being like square roots of geometry. So similar to how the complex numbers give you square roots of real numbers, spinners give you square roots of like real geometry. And we can already sort of see that with like all this double cover stuff, right? Um, in
Mhm.
some sense, when we double these things up, not double them, but like when we combine them with themselves, like when we multiply them together, we get one object. Um, in the group that we're actually interested in. Um, so yeah, I mean, it's just more that I know, like I know more spinor geometry, and I think it's cooler. So, um, but yeah, okay. So on the next problem sheet, um, I'm I'll put some of the questions that we had in today's like meeting, that I think are important. Like I think this result is pretty cool, pretty important. Um, this result is also really cool and important, so I'll put that on there. Um, and yeah, I'll ask you to prove some other things or like manifolds. You have to think about like how you want to go proving that. And yeah, if there are no other questions, I mean, do you have any other questions?
Nope.
Okay.
That's
Um,
all.
I'll post the lecture note and the videos as always. And yeah, if you have any questions, please just let me know. Um,
Sure.
and okay. See you on Saturday, man.
Yep.
Bye.
See
Bye-bye.
you.